Good evening, everyone. This is going to be the first video of hopefully many in my series on the theory of computation. Okay, so this video is just basically going to be setting the scene for sort of the sort of main branches of the theory of computation. So it's not going to be sort of as theoretical as sort of mathsy as the other videos in the series will be, but it's going to introduce fundamental questions, which effectively this entire sort of domain of math/comp sci aims to answer, and that hopefully we'll get into. So I've never actually, I had a comment about this, asking whether I teach it. I don't typically really, I've never looked at this before in my life, so I'm no expert on it, but I'm more than happy to make videos on it if it's something that people are interested in. And so I don't blame you if you don't want to watch these, but I think I'm going to make them because I'm very interested in it. Motivates me to look into things when I make videos on them. Okay, so this is going to be the first video. Obviously, about the series will also continue just whenever I'm available to make videos. Okay, but this is going to be the first video, an introductory video, so probably shorter than the average video in the series on the theory of computation. Okay, which is very, very interesting, as I hope you will agree. #1. Okay. Right. So effectively, there are three main areas of this theory, right? Okay. So there are three main areas which we need to really, which you should be aware of, right, going into it. So three main areas of this field. Okay. So they are complexity theory, computability theory, and automata theory. Computability theory and automata theory. Okay, so these are really the three main areas, and we're going to sort of start off with automata theory, then go into computability theory, then go into complexity theory. But actually, the way I'm going to introduce these areas to you is sort of from complexity theory to automata theory. Okay, because effectively by starting with sort of the endpoint, right, by starting with talking about things that we're going to sort of end off with, you'll see really what we're building up to, right, with these sort of starting theories and starting points, really, right? So obviously we're going to start off with automata theory, but we're building up to complexity theory. And by talking about complexity theory, you can get a better grasp of what we're actually trying to get to, right? What the aim of all of this is. What is the point? What's the point, right? What are we actually getting to? Okay, and hopefully I can answer, or I can sort of give you somewhat of an answer to that question. Okay, so I mean the first question, which basically links these three areas, which is of central importance to the field, is as follows. So it says basically, what are the fundamental capabilities and limitations of computers, right? So what is it that computers? Well, first of all, what is a computer? What does it do? Okay, and what does it do? What can it do? What can't it do? Right, that's basically the main question here. Okay, a very simple. Well, it's seemingly very simple question, right? I mean, it's an understandable question, which for lots of maths is often not the case, right? There's many complicated questions out there. This question's seemingly quite simple, but actually very, very, very well. It's really the question that formulated this entire theory, this entire field. So it's a very, very open-ended and very deep question. Okay, so what are the fundamental capabilities, and the limitations of computers, right? So ultimately, we want to discuss what is a computer, okay? What does a computer do, and what can it do, and what can't it do, okay? So what types of things can computers really do, right? And what types of things can they not do? And really, what types of problems can they solve? What types of problems can't they solve, okay? And of these problems, which problems are easy to solve and which ones are hard to solve, right? So that's basically what this entire sort of field is about, right? So first of all, we need to make clear what is a computer, right? What does a computer do, right? And then what sorts of problems can computers sort of solve, right? And what problems can computers not solve? Okay, that's ultimately the aim here. But that's sort of that's sort of the main overarching thing, right? This is the main overarching question which we want to basically answer to some extent by sort of the end of this entire course. Okay, and obviously it's one to think about as well. So the first, like I said, we're going to sort of start by talking about the sort of last area which we'll cover, which is complexity theory. And ultimately, complexity theory is effectively us trying to categorize which computational problems are easy to solve and which computational problems are not so easy to solve, are hard to solve. Okay, so obviously, some problems are easy, and some problems are hard, right? This is true in life as well, right? I mean, ultimately, even though we're talking mainly about problems that computers can and can't solve, what problems are easy for a computer, what problems are hard for a computer, like sort of algorithmically. Ultimately, it's just true in general that there are easy problems and there are hard problems, right? I'm sure not every problem that you've ever come across has been easy for you, okay? Or at least I hope not, because then you're doing something wrong. And some problems are hard, okay? So this is just the truth of reality to some extent, right? Some problems are easy and some problems are hard, okay? But computationally, let's think about which problems are easy and which problems are hard. So an example of an easy problem is known as the sorting problem, okay? So it's sort of self-explanatory, it sort of speaks for itself. But ultimately what you need to do in the sorting problem is just arrange numbers in ascending order in a list, okay? So if I give you a list of just randomly arranged numbers, so just numbers in some arbitrary order, you need to be able to, or the computer needs to be able to, sort the numbers in ascending order, okay? And this actually turns out to be what we call an easy problem, okay? Obviously, we're not defining these things as of right now, but just so you have an idea, really, of what sort of things we're trying to get at, right? This sorting problem, right, is effectively an easy problem, right, for a computer to solve. Let me just write down here. So obviously, the aim of the problem is to arrange a list of numbers in ascending order. Okay, numbers in ascending order. And this turns out to be algorithmically quite easy for a computer to solve. Okay, and one reason why we could make that argument, right, is because even small computers, right, even sort of very small computers, can sort, around sort of millions of numbers, right? So around sort of a million numbers, or even just millions of numbers in general, pretty quickly, actually, okay? So if I gave even a very small computer 2 million numbers in any order, it can sort them pretty easily, okay? And by pretty easily, what I really mean is pretty quickly. So computers can sort, approximately a million numbers pretty quickly, right? And so this sort of backs up our claim, right? Because right now it's only really a claim that this problem is easy, right? It's easy because even small computers can sort very, very long lists very quickly. Okay, so algorithmically, right? It's very easy to program a computer to do this, right? It's very easy for the computer to carry it out, right? So it's an easy problem, okay? Or relatively easy, obviously, to program. Okay. But an example, though, of a hard problem is known as the scheduling problem, okay? And this is a problem that probably many of you have come across in your day-to-day life. So the scheduling problem. Okay. So effectively, all this problem entails is effectively being able to schedule a school week, for example, right? So you have a school with, let's just say it has thousands of pupils, okay? And you need to be able to schedule each day of the week such that at any point in time, obviously, one room is not used by, for example, more than one class, right? That's a constraint for your schedule, right? Because you need to be able to schedule your week, so that everyone has something to do at each point in the day, or if there are free periods, then you also need to account for those and things like that, right? So ultimately, the task for the computer is to effectively come up with this schedule. So you give it a list of constraints. So you say, obviously, at any one point in time, one room cannot be used by two different classes. Okay, obviously that has to be true, and maybe other things like free periods, etc. You need to add those in, give a computer some constraints, and it needs to spit out a schedule for every class in your school for the week, right, or for however long you desire. And this problem is hard. Okay, it's not easy. It's not like the sorting problem. For a computer, this is very, 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 very tricky. Okay, even if there were sort of 1,000 classes throughout the week, it actually turns out that takes a lot of time for a computer to schedule, right? And obviously, as you add in more constraints, it will get even worse. Okay, so even sort of 1,000 classes in a time span of, let's just say, a week is hard for a computer to do. Okay, it's a hard problem because it takes a computer a very long time. Even the best computers take a long time to spit out your schedule. Okay. Right. So ultimately, which problems are easy for a computer to solve, and which problems are hard for a computer to solve? In other words, which problems take a very long time for a computer to come back to you with a solution for, right? So an easy problem, as we saw, is a sorting problem. It takes very short time period for the computer to spit out an answer, right? Even small computers can spit out answers very quickly, right? But a hard problem for a computer is one that takes it a lot of time, okay? Or at least that's one of the facets that make it hard. right? Like the scheduling problem, where even the best computers take a long time to spit out a good schedule. Okay. Okay. And yeah, and I mean, I should stress, ultimately, we're talking here about problems that are easy computationally for a computer. Okay. We don't necessarily, although it probably factors in, care about how easy or hard necessarily it was to code, because that's variable. That just depends on the person who's programming, right? At the end of the day. But ultimately, in the best case scenario, right? How hard is it for that we know of, obviously? How hard is it for a computer to? How long does it take for a computer to do these things, right? That's basically what we're getting at here. Okay, and so ultimately, at the heart of complexity theory, then we have a question, which is it's unanswered. It's an unanswered question, which is what makes some problems easy to solve, some problems easy to solve, and others hard, right? It's again a seemingly very simple question that it has not been solved. There's no solution to this question. Okay, there is no answer. Right, there's no right or wrong. Right, there's no answer to this question as of right now. So what does really make a problem easy to solve? And that's at the heart of this complexity theory, which is the last thing which we'll cover. But ultimately, you can see what we're building up to. It's what we're building up to. We want to be able to basically categorize easy problems for a computer and hard problems for a computer. Okay, we need to know which problems are easy to solve and which problems are hard to solve. Okay, and that's the aim of complexity theory right there. Okay, and obviously, as I've already said, this question is, as of right now, unanswered. Okay, and later on, obviously though, we can still explore the question, and that is what complexity theory ultimately does. It explores this question and it tries to come up with some answers to basically parts of the question, or pieces of a puzzle that can effectively get us to an answer to this problem. Okay, because you don't have the full answer, but obviously the bits and pieces that we do have, and those bits and pieces are things that we'll talk about later on. Okay, and I think it'd be interesting also to talk about like what do you do as a human being when you confront a problem that's hard. Okay, and there's a couple of things that you probably do. Okay, so and it's just nice to sort of be aware of this sort of process. So hard problems, right? So first of all, you typically probably understand what makes the problem that you're dealing with hard, right? If you come across with a hard problem, if you come across a problem which you're finding difficult, right? What makes the problem hard? Okay, because these questions are probably they're going to directly translate, right, to complexity theory and to problems that computers find algorithmically tricky, right? So what makes a problem, right? If you're finding a problem tricky, what makes it tricky, right? So this is probably these sorts of questions will be relevant later on as well, right? What makes the problem tricky? Okay, and that is effectively kind of the same as this question here, okay? Except it's obviously more specific, so easier to answer, right? Because if you have a specific problem, you can probably get to the root of what makes that problem tricky. Whereas if we're talking about problems in general, and we're talking about easy and hard in the sense of how long it takes a computer to solve them, then it's a lot trickier to answer, right? And there is no answer at the point in time. Okay, but if we're just talking about a singular problem that we face on a day-to-day basis, it's specific, we know everything about it, and we can answer this question. Okay, or at least to a satisfactory degree. Okay, so the question that you probably first ask is what makes a problem tricky? And if you know the answer to that, then you might be able to effectively alter the problem. You might be able to make it easier, okay? And in doing so, this is what we do in maths a lot, right? You make the problem easier so that we can gain some insight into the harder problem, okay? So if this is known, can the problem be made easier, okay? So that's probably the next thing you'd ask. After you know what makes it hard, you probably would ask yourself, or you could ask yourself, what can anything be done to make it easier? Okay, and then probably if the answer is yes, you can then take action, make the problem easier, and explore the consequences of the easier problem. Okay, and then explore what that means for your harder problem. Okay, so that's sort of one thing that one sort of line of reasoning that you might follow whenever you encounter a tricky problem. Okay, but equally though, you might be happy with if you're spending a lot of time on a problem and you're not getting to a solution, then you might just make some concessions, right? Sometimes we do this. We do that all the time in physics, right? Obviously, we never deal with the exact world when we're dealing with in just the sort of secondary school physics class, right? Like there's so many other factors that play a part that we just ignore. Okay, and the reason for that is because they're negligible, or they're negligible enough that we don't need to consider them. Or if not, then we're told that there are these other factors in play, and that obviously we can only model certain scenarios in certain cases. Okay, But but there are many cases where we just ignore things, right? And those are ultimately not the answers to those questions that we get by just doing maths are not necessarily the answers to the correct answer to the problem, but they're good approximations. And so it means that we make concessions, right? We don't care about necessarily getting the full answer. We care about a good approximation to our answer. Okay? So at the end of the day, if you're really, really close to an answer, you don't necessarily care, and many physicists and probably engineers don't care whether or not they are exactly on the money. Okay? Obviously, in different scenarios, you want to be more on the money, right? You want to have less of an uncertainty in your result, but ultimately, we are happy, at least in the theoretical side of things, to make these concessions. Okay? So you might accept a good approximation rather than a full solution. Yeah. Okay. So hopefully that's understood. And ultimately, you might also find a solution to a problem, right? That works, but is very inefficient in certain cases. Okay. So there might be a worst case scenario to your problem whereby actually your method will take horrendously long. Okay, maybe not horrendously long, but just a long time. Okay, if it was horrendously long, then what I'm about to say probably won't apply. But if it takes just a long time and you just don't necessarily have a meaningful method, well, to basically, well, I mean, you have a method, but you don't necessarily have a better method. And in the worst case scenario, it takes a long time. But in most cases, let's say, it's very quick. Okay, then if you have such a method to solve a problem, you might not necessarily care that it takes a very long time in the worst case scenario, right? Like obviously you want to find the best sort of thing, right? But you might not necessarily mind after a certain point in time if your algorithm or whatever works sort of 95% of the time, and 5% of the time it takes long or a good period of time. Okay, so you might also have a method which gives you not necessarily a good approximation, gives you the full solution, but it takes a long time in many cases. Not in many cases, in a few cases. And so actually you don't mind that though, right? So actually you're okay with that. And so this gives us this idea that some problems may only actually be hard in the worst case scenario. And they only be hard in worst case scenario. In the worst case scenario. In the worst case scenario. Okay? So yeah, I mean, and so, but easy the majority of the time. Okay? But easy the majority of the time. Okay, and so you might be happy with a solution that is slow sometimes but fast most of the time. Okay, you might be happy with a solution that is slow sometimes but fast most of the time. Okay, so hopefully you're happy with that idea. Okay, and the last sort of point I wanted to make, which I'll also give an example for, is that you might also settle for other types of like if you're trying to solve a problem, right, in maths, let's say, you could probably try and solve it what we say analytically, which means you're using your algebraic rules, your laws of logs, and things like that. For example, simplest case, you just have an equation. Okay, you're trying to solve an equation, a mathematical equation, and you just try and analytically solve it. And potentially, it's hard because there's not necessarily very simple analytical solution. There are many problems like this. Okay, many of them are on TikTok and things like that as well. So I'm sure you've seen a couple of them in your lifetime. Like maybe x to the x equals 5, for example, right? Or something harder than that. Like maybe some problem involving factorials, and obviously there's no neat inverse for factorials, okay? So if you try and use analytical methods, it'll be hard. It's a hard problem, okay? But then, obviously, what you can do sometimes is you can use numerical methods. So if x to the x equals 5, then maybe there is a numerical method. You could obviously rearrange that to get x to the x minus 5 equals 0. Right? And so actually maybe there's a numerical method that gives you effectively is able to calculate the roots of a function. Okay, and so if you can use that numerical method on x to the x minus 5, that equal f of x, then you could probably find the roots, right, pretty quickly, right? But if you try and solve it analytically, it takes you a long time. So you might be open to other types of sort of computation to get you to this solution. So you might settle for other types of computation. Okay, and one type that that comes up is randomness. Okay, so randomness actually sometimes is very useful. Okay, and I wanted to give an example of this because it might not be necessarily obvious what I mean. But this example is very well known, and it's called a Monte Carlo simulation. Okay, so in a Monte Carlo simulation, what you're doing is you're basically giving your computer an input, okay, and then it's using randomness in some sense, right? Randomness to basically generate something, right? Whether it could be a set of values in an interval, for example. And then what it does is you give it some formula and it puts those values into that formula, which may be a good approximation to, for example, an integral, right? So if you're trying to compute an integral, right, or ask a computer to compute an integral, then you might use a Monte Carlo simulation with a fairly large value of capital N, give it lots of numbers, okay? We'll ask it to randomly generate numbers on an interval for which you're trying to find the integral. Let's say it's from 0 to 1. Okay, so you ask your computer to give you lots of numbers from 0 to 1, and it randomly generates some uniform distribution, if you're familiar with that. If not, basically what I'm saying is just each number has an equal probability of being chosen, right? And it's on the interval, let's say, from 0 to 1. Okay, so you just randomly, the Monte Carlo simulation, you're using randomness to just pick those numbers. Okay, and then what it's doing is it's plugging into a formula that approximates the value of the integral. Okay, and then it's just sampling, it's doing this over and over again. And so eventually, obviously, with lots of sort of samples, you have a good idea of what the actual value of the integral is, without actually getting your computer to solve it. So you might settle for randomness as a means of solving a problem, okay? Because then you can just program a computer to you can use a Monte Carlo simulation, right? So let me just talk about that in more detail, okay? So here's sort of the sequence of things. So you give a program some input, okay? Some input, right? So in this case, let's say it's a function, and we'll denote that function with f, okay? And the natural number, capital N. Capital N. Okay? Now here's where the randomness comes in. Okay, so then randomness is used. Randomness. Effectively, so for your value of capital N which you gave the computer, n random points, let's say u1 all the way through to un, are going to then be generated. U capital N are effectively generated with equal probability. Okay, so uniform distribution, generated with equal probability in the interval, right, from 0 to 1, right, let's say, right, just for the sake of argument, okay, including 0 and 1, okay, but then what you might do is you might give a computer this sort of formula. So in, which is going to be 1 over capital N times the sum from I is equal to 1 all the way up to capital N of f of ui, okay. Now it turns out this is actually a good approximation, obviously, well, not obviously, sorry. It turns out this is a good approximation specifically to the integral between 0 and 1 of effectively f of t dt, right? So you can actually use this formula here, right? Which is very similar to the definition of the integral. Okay, the definition of the integral from 0 to 1 of f of t dt is actually going to be the limit as n approaches infinity, capital N approaches infinity, of effectively the sum from I is equal to 1 all the way up to capital N of f of ui and then multiplied by delta x, where delta x is effectively then going to be b minus a, in this case b, so these are the upper and lower limits of your integral. So b here is 1 and a is 0, so that's just 1. So this is just equal to 1 over capital N effectively, right? Because normally you just do the width of the interval and divide it into n equal sort of slices, right? Capital N equals slices, and you take that capital N to go to infinity. So you make it very, very large. Okay, and that gives you the actual value of the integral, right? So this is a Riemann sum, what we call. It's basically if you're not familiar with it, basically just adding up rectangles underneath the curve. Right, that's what you're doing. You're adding up rectangles underneath the curve, right? To find the area, right? And obviously the rectangles are going to be different. And obviously as you make the rectangles smaller and smaller, they give you a better approximation. Because obviously a curve is curved, whereas a rectangle is sort of not, right? So if you have lots of rectangles, you probably will miss out bits of the curve, bits of the area, right? But yeah, effectively that's the idea. Don't worry too much about it. But effectively, this delta x is just to find the sort of the width of each slice, and then the f is like the sort of height of our rectangle. So this is obviously just the area of the rectangle added up. Okay, and then we take n to go to infinity. So then what we really get is then we can pull it, and then we have 1 over n. Okay, now 1 over n is constant with respect to the sum, so you can pull it out. Okay, and what you get is therefore that integral is therefore equal to the lim as capital N approaches infinity of 1 over capital N times the sum from I equals 1 to capital N of f of ui. Now obviously this is exactly what what we asked the computer to basically compute, and then we have a limit in front, right, which you take out. So effectively, we're taking that out means that we have an approximation. Now the reason why we take that out is because obviously a computer cannot necessarily obviously the larger you give it, the more time it will take for a computer to compute it. So what you want is you want to find the right balance of a large enough n to get a more accurate result and computation time, so how long it's going to take to compute. But in reality, right, once you find that balance, then you can use this to basically give you an approximation to the integral. Okay, so in our example, that is going to give you a good approximation to your integral, right? And so you've used a Monte Carlo simulation to randomly generate values on an interval, okay, capital N values on the interval, right? Which is infinitely many values, real numbers on that interval, right? So you're always going to have another number to choose. And the idea is that then you plug it into this formula, okay, and effectively the computer just evaluates it, okay? That's it. So IN is calculated, IN is calculated, and the integral from 0 to 1 of f of t dt can be estimated for a suitable function f. Can be estimated for a suitable function f. Oh my goodness. Will this work? Okay, function f. Okay. So, right, so basically what we've done here is I've just spoken about, in all, what you really do. What do you do when you come across a hard problem in real life? Okay, so how do we actually sort of solve hard problems, and what are ways around solving hard problems? Okay, so yeah, there we go, right? And so a lot of this sort of discussion about what makes a problem hard for us and what do we do when we encounter a hard problem, will later on be able to be, we can later on effectively apply it, we can later on effectively apply it to computers, right? And what why problems, specific problems, are tricky for them, and necessarily effectively ways around that, and then what ultimately we can answer then this question, like what makes problems for a computer easy and to solve and others hard. Okay, so all this discussion obviously is very sort of non-mathematical for now. But I really just wanted to, and this is the way the textbook does it as well, so that's also why I've done it. But really, it's just that this is just sort of a discussion for you to feel the motivation for what we are building up to. Okay, yeah, and that's basically it. So you might think, where actually is complexity theory applicable? And one area where it's applicable is actually in cryptography. So the cryptography is actually quite interesting with respect to complexity theory, because because typically we look for problems that are easy. For example, maybe when you're sort of working through questions in a maths class, you probably want to start off, if you find a topic, for any topic actually, it'd be preferable, or one reasonable way about going through answering questions is by starting with the easier questions, right? And then moving to the harder ones, right? And even then, the harder questions, they're still probably decently solvable by yourself. Okay, so you're never really looking for, really, really hard, unsolvable problems that no one can do, right? Probably in your day-to-day, you look at problems that are hard for yourself and challenging for you, but probably not necessarily unsolvable for the majority, right? But actually in cryptography though, we actually do look for hard computational problems, specifically computational problems. I've obviously made this analogy between humans and computers, but obviously with complexity theory, we're talking about computers, computational problems, algorithms, things like that. And obviously cryptography loves these sorts of things, okay? And it loves hard computational problems. So this thing, cryptography, it loves hard computational problems. Hard computational problems, right? So any problems that exist that are hard to solve computationally, okay, or take a very long time for computers to solve, in the best case scenario, are really what cryptography loves. It needs to find those problems, right? Because right now we don't necessarily have an answer to what makes problems easy to solve for computers and others hard to solve for computers, right? Don't necessarily have a buy and gone answer to that question. There's no direct, complete answer to that. Okay, but we have made some progress towards an answer. Okay, and so there are sort of ways for us to sort of see which problems are hard and which problems aren't. Okay, and it's those problems that complexity theory can help us find that are hard that cryptography needs. Okay, you might ask, why does it need these? Well, hopefully you probably already came up with the reason yourself as to why cryptography needs these problems. But effectively, cryptography deals with sensitive information, right? Like details that probably you don't want other people finding. Okay. And even when for example, when you're talking to someone online, there is sort of some data there that is probably is being transmitted, okay? And obviously you don't want someone to intercept your conversation at random. And so that data has to be encrypted, okay? If it isn't encrypted, then someone can access it, right? So you don't want that. But the way that it's encrypted is influenced by these problems that are hard, because effectively, if someone were to try and crack this sort of encryption sort of key or whatever, then it would take them a very long time, even with the best computer, because these are hard computational problems. Okay, so there we go, right? So that is ultimately why cryptography needs hard computational problems, okay? Why that's sort of kind of unique to cryptography as a field, okay? Obviously, lots of mathematicians look at unsolved problems as well for their own sort of furthering of the field, okay? But yeah, cryptography is one of those fields that's interesting because it needs those, okay? It needs to have those hard problems. Okay. Yeah. Right. So the next part that of sort of the theory of computation, which is sort of the second thing we'll look at. So there's obviously three sections. This was the last. So we'll look at this last later on. But the second one, which we'll look at a little bit before this, is computability theory. Okay. So this is going to be shorter than complexity theory. That's by far the longest explanation I'm going to make. Okay. But ultimately, what we do know for sure, okay, something we do know for sure, is that certain problems cannot be solved by computers. Okay. So there are problems out there. There are things out there that we know computers cannot solve. Okay. No matter how good the computer is. Okay, cannot be solved by computers. Okay, unfortunately, that's the reality. Okay, so some problems cannot be solved by computers. Right, and a good example of this is actually quite a simple problem, which is determining whether or not a mathematical statement is true or false. Example: determining if it lets me write this, determining whether a mathematical problem is true or false. Okay, you might think, wait, how is this impossible? Okay, and obviously on the most part, right? Like obviously now we have things like ChatGPT and AI that can probably do this very well, but still they cannot. It's a problem that cannot be solved, right? So no computer can do this with 100% accuracy. Okay, no, not even the best AI. Okay, because there are problems out there which even we don't know the answer to. Okay, so AI is going to search through and sort of check to see if there is a proof. But currently it's not capable of coming up with proofs. Okay, so it's not really good enough in that sense, right? And so if I or I should really say mathematical problem, just a statement. Sorry, mathematical statement. Okay, and so obviously if I give it a statement, right? For example, let's say I give it the Riemann hypothesis, or like a conjecture, right? Then it cannot tell me. AI, ChatGPT cannot tell me is that problem true? Is that statement true or false? It can't tell me that, right? Because it doesn't know that. Even we don't know the answer to that. So neither will ChatGPT. Okay, but no reasonable computer at all will ever be able to determine, in general, right, whether a mathematical statement is true, whether every mathematical statement that you could possibly give it is true or false. Okay, unfortunately, and also this also gets into sort of some weird stuff with Gödel as well. If you don't know, he's a logician, famous logician, who proved a lot of very interesting things to do with logic and maths. Okay, so a lot of this stuff will get a bit more complicated as to why this is not possible. But just intuitively, just gave you the example with ChatGPT. Because that's something that came into my mind. We have ChatGPT, but then obviously I wasn't thinking about the hardest of the hardest problems. Right, even ChatGPT will either not get them correct, or spend infinitely long trying to find the proof, or just say it doesn't know. Okay, so even ChatGPT cannot do this. This will never be solvable by a computer. Okay. All right. Now, the most important thing though is that you understand the difference between this and complexity theory. Okay, so complexity theory, what does it aim to do? Complexity theory, effectively, the main aim of complexity theory is to sort problems into those that are easy to solve and those that are hard to solve. Into those easy to solve, and obviously we're talking about compute, like for a computer to solve, right? So in terms of the time it takes for a computer to solve it, so it aims to sort problems into those easy to solve and those hard to solve. Okay, so that's the main aim, right? So that's what we were just talking about before. Okay, but computability theory is different. Okay, and it's interesting in the way that it's different. Okay, because what it aims to do is actually classify problems into those that a computer can solve and those that a computer cannot solve. Okay, so there are problems out there that exist, obviously, that we've already seen one example here, and although I haven't obviously proven to you that it can never be solved, but obviously we will have a look at this sort of thing later on, just now giving you sort of a feel for the field and for the subfield really of the theory of computation. So obviously there are problems that are out there, right? Unfortunately, or maybe even fortunately, probably for us now, with the way that things are looking, that computers just cannot solve. Okay, it doesn't matter how good it is, right? Just not possible to solve. Okay, so computability theory aims to identify these. Okay, so it aims to classify and identify problems that a computer can solve, right, versus problems that a computer can't solve. Okay, so those are the differences. So complexity is problems that are easy for a computer to solve, so and take very little time, even for very sort of small computers, and hard to solve, so take very long time for the best computers. Whereas computability theory is different because it aims to identify problems that a computer can solve versus problems that a computer cannot solve. Okay, so that's computability theory. And the last sort of thing I want to talk about, which is really the first thing that we're going to delve into when we do talk a little bit more about this, is automata theory. Okay, and this is probably where most people begin the theory of computation. Okay, they don't start with computability theory, complexity theory. They start here with automata theory. Okay, and the reason why is because before you even deal with these problems, right? What problems can a computer solve? What problems can a computer not solve? Which problems are easy for a computer to solve? What's hard? Before you even answer those questions, you need to talk to yourself and say, what actually is a computer? Okay? And what does a computer do? Right? Because if you don't know the answer to that problem, then you can't even answer. You wouldn't be doesn't nowhere near the answer to the next ones. Okay? So automata theory effectively aims to formally define and talk about the properties of effectively mathematical models of a computer. So even before we actually had computers, obviously now I'm recording this on a computer, but even before we had computers, there was a mathematical model of what a computer is, which actually influenced how we built computers, right? So mathematics is really behind everything, okay? And ultimately, it was sort of this theory, right, automata theory, that sort of came up with definitions for what a computer is and a mathematical model for what a computer is and what it does, okay? And obviously nowadays, automata theory, therefore, plays a very, very big role in many areas of applied computer science. Okay, so obviously at its heart is a theory; it's theoretical, but actually, obviously, the theory can be used to actually produce real life things, right? Like this computer that I'm recording on. Okay, so it can be applied to computer science. Okay, so those applications exist, right? So I mean, what I really should just say is to talk about what is automata theory. I should write that down. So automata theory deals with the definitions and properties of mathematical models of computation. Okay, and as you would expect, these models are quite complicated. Okay, so we're going to have to go through prerequisites. Okay, which is going to be the next video before we really start getting into the details. Okay, because this is quite obviously as you would expect, right? You would hope it's quite complicated. Actually, I don't know if you would hope it's quite complicated, but it is complicated. Okay, so there's a lot to it, right? And hopefully you stick by till the end. But ultimately, automata theory deals with definitions and properties of mathematical models. Of mathematical models of computation. Okay, right? And so, as I've already said, these play lots and lots of roles in applied areas of computer science. Okay, so coming to the end here. And this is as I was saying, to really understand computability and complexity theory, you obviously must first understand what really is a computer, okay? Which is really outlined in automata theory, okay? And so this is really just the beginning. It's kind of the first stage, and it allows us to basically get used to and practice these formal definitions of computation, right? So what a computer is at its heart, right? And obviously then these concepts that we're introducing in automata theory, we can also obviously apply them in different areas of computer science. So obviously we'll also be introduced to things that we can apply to the real world. So it'll be quite interesting in that regard. Okay, thank you guys very much for listening. That's going to be today's video. This is just an introduction to the theory of computation, which I think is necessary. I think you do need an introduction to this because it's not necessarily obvious. Obviously, it says a theory of computation. There's a lot of theory. But what really are we talking about? Okay, and actually, when you find out what we're talking about, you realize that it's actually a lot more interesting than what you probably thought. Okay, very, very cool. And hopefully, you'll stick with me till the end. And I'll see you guys in the next one. Goodbye.